All right, so here's part 3. So if I'm looking at a coffee cup calorimeter, that means I'm putting something hot into something cold, or something that's releasing energy, and the water or the solution that's in there is going to be absorbing the energy. So I know that it's going to be Q lost is equal to negative Q gain. Now, we started at 24.6, we went to 31.3, so that means it's going to be an endo or an exothermic reaction. Exothermic. Temperature went up, it got hotter. Okay? So my Q lost is going to be my delta H of the reaction. The reaction is what's supplying the energy. And it's going to equal the mass of the solution times the specific heat of the solution times the change in temperature of the solution. Now, here's where we got to look at some of the things. This is, we almost always, we put 100 milliliters in 100 milliliters. So what's the final volume of my mixture in the calorimeter? 200 milliliters, right? So that's how much, once you mix them, that's what's going to absorb or release the energy. So we're going to use all 200 milliliters. Then it says that the density is 1. So 200 milliliters is going to be how many grams? Get your calculator out if you need to. 200 times 1 is going to equal 200, okay? So 200 milliliters is going to be 200 grams. And they generally keep the specific heat the same as just as if it was pure water. Okay? It's not really going to be the same, but these problems, I always simplify them to make them look like that. So I just simply say that the mass of my solution is 200 grams. The specific heat of the solution is 4.184 joules per gram degrees Celsius, times the change in temperature, which is always going to be final minus initial, 31.3 degrees minus the 24.6 degrees Celsius. When we do all of that, delta H turns out to equal 5,606.56. Okay? That's not kilojoules. Notice grams cancel, degrees Celsius are going to cancel. That's going to leave me that many joules. And it's going to be, because this is negative, and I didn't put my negative in here, there's a negative. It comes out negative every time. Okay? Because Q loss equals negative Q gained. So the heat gained by the water, 5,606 kilojoules is what's gained by the water. 506 joules is what's gained by the water, which means that that's how much heat was given off during the chemical reaction. Okay? Now, we really should write a chemical equation for this, but they just asked for the overall heat on this particular question, but it's HCl. What's that going to make? NaCl and water. So it's 1 to 1. So notice the answer is given in kilojoules, and we have 2 sig figs. Why do we only have 2 sig figs? Everything's given in 3 and 4.
Because when you subtract out like 31.3 and 24.6, you get 6.7.
6.7 degrees. So that is only 2 sig figs. So my answer is equal to negative 5.6 kilojoules. Now, a lot of times these problems, this particular one is not asking for this, but a lot of problems will say, okay then, part B, what would be the delta H in kilojoules per mole? Okay? So B, what is delta H of the reaction in kilojoules per mole? Well, how can we do that? This is kilojoules per how much?
For 200 grams.
200 grams of the solution, right? Okay, but we have to do it in terms of moles of this one or moles of that one. Okay, so we'll do in terms of kilojoules per mole of NaOH. So we combined, and see in this one now, you're just going to use this part, because that's how many moles that we put in. So how do I convert this negative 5.6 kilojoules? This is per 100 milliliters NaOH. All right? Negative 5.6 kilojoules per 100 milliliters.
I thought it was for 200.
Well, but of the NaOH.
Okay.
All right? For the delta H, but it's per 100 milliliters of the NaOH that you put in. So now, what do I do? Any suggestions? What units am I going for? Kilojoules per mole. How do I convert? There you go. We use the molarity, and the molarity is 1. Okay? But we first have to convert this by saying 1,000 milliliters over 1 liter, and then times the molarity of 1 mole per liter. And so that's really just going to make this 0.1. So it comes out to 56, right? So if you were to put a mole and react to a complete mole of NaOH with enough HCl to react with it completely, you'd expect negative 56 kilojoules to be released. Now, with the temperature change, if you added more, obviously you're going to have to add, a liter to get a mole. And so that means that there are more heat's released, but the volume is greater, so temperature change will be different and all those things. So if we ever have to find kilojoules per mole, you're just going to have to figure out, well, this is kilojoules per whatever they're asking the moles of. And then you just convert that to moles and use the conversion factor from there. And that's why solution chemistry is going to come into play on this one. All right. So that was a good one. And we could do the same thing. We could do kilojoules per gram as well. And then just use the molar mass and convert it to grams and do kilojoules per gram as another way. Sometimes they do joules per gram and then kilojoules per mole. It's all just setting your units up. All right, so let's look at, I want you to practice this one then. This one's a flashback. This one really applies to the previous type of problem. All right, so it's a very straightforward problem. 5.8 grams of methane. Change that to moles using the molar mass of methane. And then use the given 890. Now, notice that it says it's released. So released means endo or exothermic. Exothermic. If it said absorbed, then it's going to be endo. Okay? So, I'm trying to read, there's a word that they sometimes use for released that confuses kids, and we'll come across one that says that. All right, so that one, what is this? Does it come out to
Negative 320.
kilojoules? Okay, so that one's real straightforward. Notice it's not talking about putting anything in to a calorimeter. It just gives you the heat of the reaction. All right, but the next one on the next page. Let's try that one. You guys do this one. First thing you always want to do is make sure you write a balanced equation, because you need to know what the coefficients are. So what would that make? And that's my precipitate plus 2 NaNO3s. And we know it's alkali metal and a nitrate, so I know it's going to be aqueous. So it is 1-to-1. Yeah.
Yeah.
Okay, do we know what to do? What's the overall final mass of the solution gonna be?
2,000.
2,000 grams, because it's gonna be 2 liters or 2,000 milliliters, which is 2,000 grams. Okay? Now, just because they're asking per mole of BaSO4 formed, well, how many moles are we adding in here? 1 liter times 1 mole per liter. This is 1 mole plus 1 mole. So I know I'm going to get 1 mole of this. So this energy change is already going to be per mole. If it weren't, we would have to figure out how many moles of this, figure out a limiting reactant, and then figure out how many moles of this actually got made. And then we could figure out divide that and get kilojoules per mole. But since it's 1 mole, it makes it a lot easier. So my delta H of the reaction is going to equal MC delta T. And so the mass of the solution we just said was 2,000 grams. Specific heat, they say assume at 4.18. Then the change in temperature, the solution went from 25 to 28.1. So 3.1 degrees positive. So you just multiply that out to 2 sig figs. Negative 26, is that gonna what? It's gonna come out to 26,000. Negative 26,000 joules, which is equal to negative 26 kilojoules, and that's per the mole of BaSO4. So if it's not nice and even like this, we just have to do the stoichiometry math in order to be able to figure out how many moles it was. So if it wasn't 1 mole, if this came out to 0.25 moles, we would just take this answer and divide it by 0.25. And that would give you kilojoules per mole. Okay? So you just do this normal stoichiometry to figure that out. All right. That's the second way, calorimetry. And that's what we're going to, hopefully, we'll do a lab probably at the beginning of next week. We'll probably end up doing on Monday, Tuesday. You know, everybody that can do it in person, do it in person. Like y'all would then on Tuesday maybe have a set of problems to work on. Wednesday would be everybody doing the lab report, working on that. That's probably how things will pan out because we need to do a lab with this. Okay, so we're all comfortable with calorimetry. Biggest thing is when you put solutions together, you have to add the total volumes, but when you do it per mole, you're going to just do whatever they're asking the moles of. All right, the third way. Just to be concise. Missing a page. Page 7. Oh. This is what I was looking for. All right. So we have, if I'm right here, am I on the screen? Delta H of the reaction is just a general form. Sometimes we can say we have delta H sub F, and then when we put the degree symbol up here, this means standard conditions. And standard conditions for anything but gases is going to be still 1 atmosphere of pressure, but it's going to be 25 degrees Celsius. So that degree symbol always means standard temperature. So if you see that, that's going to tell me it's standard conditions, so I automatically know the temperature. This is called the heat of formation. And a formation reaction is the elements combine to make a molecule. So example would be hydrogen plus oxygen. Well, actually we're going to go halves because it's always per 1 mole. Goes to H2O. So the formation is, you make a compound from the elements in the natural state. How much energy is released or absorbed during those transformations? Okay, so for glucose, okay, glucose is C6H12O6. So to make one of these, we're going to need 6 carbons. And by the way, the natural form of carbon is graphite. Plus, we're going to need 6 hydrogen gases. And we're going to need 3 oxygen gases to combine to make 1 glucose. So the heat of formation of this is how much energy is released when that's formed. Now, we don't know how much energy is present in any particular substance. We already said that about a piece of paper. What scientists have done, and the way we kind of get around this, is they assume the heat of formation of an element is 0. Because elements are already formed. They're there. But so they're comparing, does the compound have more energy or less energy than the elements in their natural state? If it's positive, they have more energy. If the heat of formation is negative, they have less energy. They're more stable. And so everything is comparing the compound to the original elements. But we're going to say then that that's a built-in amount of potential energy that that molecule has. That's its internal energy. So 0 for elements in their standard states. Okay? You're just going to have to know that. So it won't ever be on this table. But when I look at water, negative 286 kilojoules per mole, when hydrogen and oxygen make 1 mole of water, I can expect negative 286 or 286 kilojoules to be released to the surroundings. We know hydrogen is very flammable, so when hydrogen and oxygen burn, they give off a lot of heat. Okay? C6H6 isn't on there. So, but if I'm going to make ammonia, nitrogen plus hydrogen make an ammonia, only 46 kilojoules is going to be released. It's not nearly as an exothermic of a reaction. But to make NO2 gas, you actually have to put energy in. The product is less stable than the reactant. Now, there are other forms of delta H. We can have delta H of combustion. That means it's just going to be a combustion reaction. Combustion means what? Burning, combining with oxygen. You can have delta H of neutralization, which is what that previous problem, we added the HCl and the NaOH together, that was a neutralization. So sometimes rather than saying delta H of reaction, they'd say delta H of neutralization. So a lot of times the little subscript down here just describes what type of reaction you're calculating the delta H for. But delta H is delta H, and we calculate it all the same way. Now, this person, I don't know where they came up with the name of this formula, the Big Mama equation. But this equation is probably the most important equation in thermochemistry. Now, AP has kind of gone away from this and done way more calorimetry type problems in recent years. In the past, this was the main equation that we used. So there's been conflicting information to me as far as whether or not this is still even going to be used directly, but I think on the last test, I saw a problem like this, so we're going to go through this. This is really relatively easy, okay? So if you look here, this is delta H of the reaction is just going to equal, what does this symbol mean? Sum of, okay? So this is the sum of the heat of formation of products minus the sum of the heat of formation of reactants, okay? Because delta H is a state function, it doesn't matter what path you take. So as a result, we can go through and we don't have to know the delta H of formations of each thing. We can assume that's the potential energy in each thing when we go to the table and we just find delta H of formation. Okay? So it's just going to be a really straightforward type problem. So if we look, do I want it? Okay, we can just go to the next page. Keeping that equation in mind, I wish I could keep both on here. So we know here, the equation, the Big Mama equation, delta H of a reaction is equal to the sum of your heat of formations of products minus the sum of your heat of formation of reactants. Okay? This table is your values for heat of formation. These values will always be given to you. So, when we go and look at this then, delta H is equal to, I'll say delta H of the reaction. We go to products, Al2O3, okay? Well, Al2O3, the heat of formation is negative 1676. So it's going to be, and there's only, the coefficient in front of it's a 1, so it's going to be 1 mole times negative 1676 kilojoules per mole. Plus 1 mole, and if it's a 1 like this, you really don't have to write it, I'm just making a point. AlCl3. AlCl3 is given as negative 704. Plus NO. The NO is plus 90, but we have, this is kilojoules per mole, but we're making 3 moles. So it's going to be 3 moles times the 90 kilojoules per mole. Plus H2O gas. Some of the energy was 296 or something like that for liquid, but some of the energy is used up to break the bonds to make it go to the gas, so it's not as high. But it's going to be 6 moles times negative 242 kilojoules per mole. And all of that is strictly the sum of the heat of formation of the reactants, of the products. Now we have to do the same thing for the reactants. But what do we know it's going to be for aluminum? What's the heat of formation? It's not on the table. Okay, that wasn't a very confident answer, but why, that is the correct answer, why 0?
Because it's a pure element.
Because it's an element. The heat of formation of any element is 0. So delta H is equal to 0 for aluminum, so we don't even have to include that. So this is going to be minus, the only other reactant that we have is this one, and that's given as negative 295. But it's 3 of them, so it's 3 moles times negative 295. So then, it's a kind of complicated, to put in your calculator, but you can really just put it into your calculator just exactly the way it's written. Negative 1676 minus 704 plus 270 plus 6 times negative 242. I'll probably hit equals, and then minus 3 times negative 295. You can just plug it all straight into your calculator. Oh man, we gotta do that. This. Did you get an answer?
Negative 2,677.
And that's going to end up just being kilojoules. That's the amount of energy that's released during this chemical reaction. So listen, this is per 3 moles of aluminum that react. This is per 3 moles of this. So if it wanted to find, given the information, calculate delta H for the reaction, but if it said in kilojoules per mole of this, or kilojoules per mole of aluminum reacted, we'd have to divide this by 3 moles to get kilojoules per mole. So you have to read the question. Is it asking for the overall heat of the reaction, which is this, or is it asking for kilojoules per mole? So it's asking kilojoules per mole, you just got to go and divide by the coefficient. Okay? So these values are always going to be given. Now, the only variance on these problems is like this next one. So it says occasionally not all of the values are found in the table of thermodynamic data. For most substances, it's impossible to go into a lab and directly synthesize a compound from its free elements. The heat of formation for the substance must be calculated by working backwards from its heat of combustion. Calculate the delta H of formation of glucose given the combustion reaction above. So here's my reaction, okay? But it says now that what is this telling me right here? What is that value?
That's the heat of reaction.
That's the heat of the reaction. But what sign is it really going to be for delta H? Negative. Okay, because it's exothermic, because it's on the right-hand side, when we plug it into this equation for delta H, it's going to be a negative value. Are y'all good with that, to understanding that? Okay? Am I on the screen over here?
Yes.
Yeah, I thought I moved it back. Okay, so what's going to be different about this problem? Delta H equals the sum of the heat of formation of products minus the sum of heat of formation of reactants. What's different?
The products have more energy, I think.
Well, yeah, but
We already have we're working backwards.
yeah, we're working backwards. We already have delta H. This negative 2800 is the delta H. So it's going to equal the sum of the heat of formation of products. So my products are going to be 6 moles of CO2 times 1 mole of the CO2 is negative 393.5 kilojoules for every 1 mole, plus the water, which is going to be 6 waters, times the negative 285.8. Okay, so that's the heat of formation of products minus the heat of formation of reactants. Well, what's the heat of formation of C6H12O6? That's what the question's asking for, right? That's my unknown. Now I only have 1 mole, so it's going to be 1 mole times my delta H of formation, C6H12O6. That's my X. That's my unknown. And so if you want to just write in 1X or just X, that would work just as easily. But I just want to make sure you know what you're looking for. Plus, this isn't given in the table either. What's the value of oxygen's heat of formation? 0. So it's plus 6 times 0, which obviously is a moot point. So really the whole reactant side is just my X. So now you just got to go through and do the math. Multiply it out, subtract it out, divide out, and solve for X. What do we get for an answer?
Negative 1276.
Negative 12.
76.
76 kilojoules, and that's per 1 mole of glucose that's formed. Okay? So, if we're looking at units on this one, moles cancel, so I have kilojoules. Moles cancel, so I have kilojoules. I have kilojoules here, so when I collect my terms, it's kilojoules. But then I'm going to divide by the 1 mole right here, and that's going to give me my kilojoules per mole, because I have to divide by, even though it doesn't change the number at all for units purposes, that's where this mole's coming from. So again, if this was a 2 or a 3 or a 4, we'd be dividing by 2, 3, or 4. All right? Okay, let's open your book then, and on page 208, let's just use the rest of the period to work on. Go ahead, turn right to it. 74A and D, and 75. is, it's way in the back.
Mine was out.
Yeah, it's used a lot. What page is it on?
1100.
Page 1100 in the back of your book. So those of you at home doing these problems, I know that you're doing them on your own, okay? You need to go to the back of your book, page 1100, to get the values for your delta H's on these. And we'll go over these next class.